Hello, this is the presentation to the optimal FEA design with Wittenstein and Schneeberger components. And this is our use case. What you can see here is a use case that I got inspired from the Wittenstein catalog. You can see here machine bed, and on top of it some linear guides, and of course a carrier, and on the carrier mounted you can see a Wittenstein planetary gear. When you look at this design as a engineer, you probably ask yourself, or this is actually a most common question: what should be the optimal size of the used components? What should be the optimal repartition or distribution of mass and stiffness in my system? And of course, you have a lot of different sizes of Wittenstein planetary gear that you can get, and the same thing is true for the Schneeberger linear guides. So you got actually a lot of possible combinations. And if you are an engineer, a very experienced engineer, you probably already know approximately what size you should use, but basically it's always a very good idea to check your design before building the very first prototype. So it's all about the right distribution of mass and stiffness, and this is one of the most important factors in the design of machine tools. And of probably now you're already thinking if it's about mass and stiffness, and you already heard about eigenfrequencies. Eigenfrequencies are determined by mass and stiffness, so it's also about eigenfrequencies, which are very important. And prediction of eigenfrequencies before the prototype is built is very crucial. Now, the finite element analysis is the most exact way to predict eigenvalues and eigenfrequencies of structural assemblies. But because when designing machines, we have a lot of different design variants, we need efficient finite element modeling and simulation of those design variants. And this is what we call scalable FEA. What is scalable FEA? Here you can see on the horizontal axis the number of design variants, and on the vertical axis you can see the analysis effort needed to get to a simulation result. And the red curve is what we call the non-scalable FEA, where the analysis effort remains the same, it's constant, no matter how many design variants you are simulating. And the scalable finite element analysis is basically the green curve, where most probably the effort needed for to model the first design is probably slightly higher than in the case of a non-scalable finite element analysis. But when you get to your second and third and fourth design, the effort drops dramatically to almost zero. Meshparts is the only provider of scalable finite element analysis of machines. And I think it's very interesting to take a look at this diagram. Everything started with a drawing board, and as the computers are getting stronger, we moved from 2D CAD to 3D CAD to finite element analysis. And also notice that somewhere after the strong development of 3D CAD, we see CAD libraries introduced. Names like trace parts or cadenas should be known. And the way we see scalable FEA is as the next step after the development of FEA. And we do this by introducing the so-called finite element model libraries. Now this is the point where I would like to show you how these finite element model libraries are implemented in the MeshPath software. Here you can see the MeshPath software. First of all, on the left side, we can see a directory structure, and here this blue folder is the MeshPath library of components. You can see here two main directories. One is called standard components, the other one is special components. Standard components contains the machine toolbox library, which contains most of the parts needed to model machine tools. The special components directory contains manufacturer-specific components, and in our example, we are using the Schneeberger linear guides and the Wittenstein planetary gears. Let's take a look at the Schneeberger library. You can see here the wagon and the guides. And the wagon already contains some variants of the library. Those are ready-to-use parametrical finite element models. So basically, if I open this model, I can take a look at it, and I can see also that it has some model parameters. And one of the most important parameters is the name of the product, as you can see it at the manufacturer. And also, the whole library is implemented through tables. You can see here geometrical parameters, but also very important for the simulation is is physical data like mass and stiffness curves, as you can see here. Also, you can see there is a lot of data, and if you do this manually, then this is a very big effort. Finally, let's take a look at the Wittenstein library. You can see here the planetary gear, TP, also some pre-generated models of the gear. Let's open this model. Also, this library is implemented through tables, and you can see that this specific variant has these parameters here. Here we have the total mass, here is the rotational inertia, and here is the torsional stiffness of the gearbox. Also, this is the transmission ratio. So this is the main difference between a CAD library and the finite element model library. In the CAD library, you only have geometrical data, and the model of a planetary gear or of a linear guide or whatsoever is not usable in a finite element simulation. So we cannot really use CAD libraries in the finite element simulation. So this is the reason why MeshPath implements all those libraries of machine components in order to accelerate the modeling process and simplify the modeling process, and also reducing the probability of doing errors when parameters are input by hand. Also, I would like to show you how the catalog of the manufacturer looks like, and this is what you would do when not using a finite element library. This is where you are looking, and for example, you can see here some nonlinear stiffness data, and the point is this is just a picture. So if you want to use this data in a finite element software, you would have to somehow convert a picture into numerical data, which is really very time consuming. Same thing for the Wittenstein. They are not providing though nonlinear data. You have here some linearized torsional rigidity, for example, but still, this is a big effort in when performing FEA of machines. You really have to gather all this physical data from the catalog and put it into your model, and the modeling effort doesn't really scale with changing the variant, because you have to do this every time you need a new variant of this of these components. So going back into the MeshPath software, what we did is to create a simplified version of what you saw in the second slide of my presentation. So what we modeled is this carrier plate, the Wittenstein gearbox, and we put here Schneeberger linear guides. This may look like a very usual finite element assembly, but it's not, because the whole model is component oriented, as everything in the MeshPath software. You can see here we have a component for the carrier, another component for the gearbox, and another component for the wagons. And those components are just copy pasted into the assembly. So it may look more similar to a CD program than to a typical finite element software. Also, each component has parameters that can be easily changed so that the model will adapt very quickly to your new configuration. Now let's take a look at the so-called assembly equations. In order to speed up things and quickly and being able to quickly change design variants, we have defined here three main parameters. One of these is the first parameter is the variant name of the Wittenstein planetary gear. The second parameter is the variant name of the Wittenstein pinion, and the third parameter is the variant name of the Schneeberger linear block used. Also, we have another parameter. This is the thickness of this plate here. And you can see also that we are using those parameters defined in the assembly in the parameterization of every single component. You can see here the thickness defined as a parameter. Also in the planetary gear we have not input a string or a name. Instead we are using the previously defined parameter name. So now we have a full parametric finite element assembly, and we want to know what is the best combination of Wittenstein planetary gear and Schneeberger linear guides. For this, we have defined a so-called factorial table and design factors. You can see here that the variant names and the thickness are different design factors, and those design factors have different number of values that can be taken. And we have here a factorial table. The factorial table contains the values for every design. So we have here a total of 27 designs, and we can now automatically generate a design for each single row in this table. We can also activate different designs. For example, I can go and select a specific design, and as you can see, the whole assembly will adapt to this new design. And it's also very quickly, and the whole physical data is imported from the library, so there's really no modeling effort here. So this is what we mean, what we understand as a scalable finite element simulation. When you want to analyze your design, you can for example, focus on one design and say, okay, I just want a model analysis where I can compute my eigenfrequencies. This can be done very quickly. You can solve this, and you can see here a small window popping up. This is ANSYS, because MeshParts is computing the solution for the finite element models using the well-known ANSYS solver. And when the solution is done, I can see here a message, and I can go and visualize the results. Just wait a second, and here's where you can see the last eigenfrequency, and I can select another eigenfrequency, but what's important for me is actually not the last eigenfrequency, but the first eigenfrequency. So let's go and select this one. You can see the first eigenfrequencies occurs at 210 Hertz. This is a deformation of the plate and also of the gearbox. So for me, it looks like the gearbox should be a little bigger, and probably also we need a thicker plate here. But the question is, what is the right combination again? So instead of changing manually the model and creating a new simulation and then taking a look at the results, it's much more efficient to work with this automatically way of MeshParts, of generating models based on a factorial table. So what we do now is to simply click here on generate models, and this action will basically generate a new model for each single row in the factorial table. You can see how models are added gradually to the library. Now this will take a few moments because we have a total of 27 designs. You can see here how the active design number is changing and updating. It's probably a good idea to not show the results during this model update. Yeah, because of course the results are not really matching the new model. Now you can see a design where the gearbox is very small. So now the whole thing is finished. We have created 27 variants of this model, and now what I want to do is to select all those 27 designs and simply say solve from the context menu. Again, you can see how an ANSYS batch process is popping up. Every single design will be solved, and you can see here in the output window a message telling you that the solution job was finished for this specific design. Also, we have to wait a while because it will really take a few minutes in order to finish the whole all the solution for all the designs. Okay, it looks like all the designs were solved. So the next step is to take a look at the eigenfrequencies, and the first eigenfrequency is of course most important, and we will simply select again all available designs here and select retrieve parameters from the context menu. A new window will open where I can see for every single model the value of the first eigenfrequency. Um, it's simpler if we copy this table and open Microsoft Excel, defining a new table and then just copy pasting the values into the table. Now go to the insert menu and insert a new diagram. It's very nice to see how the first frequency is depending on what kind of combination of gearbox, planetary gear, and linear guide is used. You can see this is a very non-linear behavior, and our optimum should be somewhere here. You can see that from the original design, starting at 200 hertz, we get over 300 hertz as for the first frequency, and this occurs at the DOE design of experiments 15. So the 15th design is our winner. We can see it here, and what you can do now is to select from the text menu visualize results, and this will be the last eigenfrequency, which is not so important. Let's go and select the first one, and the animation and the deformation plot will show you how that the deformation basically remains the same, but because now we have the right combination between mass and stiffness, this design is much better. We have 50% more dynamical stiffness in our system. So we can also animate the result in order to better understand how the system will vibrate. This is it. You can see how the pinion is rotating. You can see how the plate is deforming and how the linear wagons are displacing. Also, it's possible to, for example, only display the planetary gear. This is also no problem at all. Or you could also display only the plate, or you could say I want to see both of them, or again show the whole system. Okay, that was it in the whole demonstration. Let's summarize the whole thing. We have a very interesting use case where the first eigenfrequency strongly depends on the size of the used Wittenstein and Schneeberger components. So it's all about the right combination between mass and stiffness. And our method, in order to efficiently analyze different combinations, different design variants, is to use the so-called scalable finite element analysis, where the modeling effort is dropping dramatically after the first design. And we do this by introducing the so-called finite element library at the Meshparts company. I hope it was interesting to watch, and see you next time. Bye.